sorry, I will. Okay. So there exist two kinds of principal motives: the decrease in value of energy bills and the increase of patrimonial value of housing. So we focus on this second point. Previous research focusing on patrimonial value has shown for the a positive effect of renovation and of energy performance on housing prices. Nevertheless, we identified heterogeneity that are focused on periods and spatial units difference, in particular in Europe, Asia, and North America. And to the best of our knowledge, there are few studies using a temporal dimension. So we have statistical results for the most of these measures.
I'm sorry, Natalie, to interrupt, but we see only a black screen. So
oh, God, sorry. Okay, I don't know what's.
Maybe you can try to start again the presentation again. We see your screen.
Okay.
I think it's an Apple computer, is it?
Yes.
So, but the presentation is black.
Oh, sorry. How can I do? Maybe. Okay.
We see the title also, the title of the file.
Okay. Sorry. I will try to.
Yeah. Try again. Let's try again.
Okay. Can you see?
Yeah. Perfect. Perfectly.
Okay. So here we start with the canonical model. So I say that we presented that on different kind of studies. So here we analyze first on a canonical model this phenomenon of valorization of energy performance for the rental market, and we base on the model as Rosen in 1974 that has been developed for composite goods, non-homogeneous goods as housing. In this model, the service of the house depends on a vector of age attributes, and here we focus on the attribute energy performance. So I don't know if you can see. It's okay? Okay. So
it is perfect.
Thank you very much. In this model, we have two kinds of agents, landlords and tenants. And tenants choose their house in order to maximize their utility. It depends on the consumption of energy performance service, HN, plus other goods. And the condition for preferring the house with a level HN to a house of level HM is represented by this equation that depends on the difference of prices between both under the difference of energy quality. And this alpha that represents the parameter of preferences for energy performance quality is bounded by alpha mean, alpha max, with F, its cumulative distribution function. Okay. So in the case of landlords, they seek for the highest rent from property. And there is an equilibrium if the proportion of tenants asking for a house of type HN amounts exactly to theta n, where theta n corresponds to the share of houses with a given energy performance HN. So for the first one, for the lowest energy performance service level, H1, the price is represented by alpha mean, the lowest condition for preference for energy quality that multiplies the level of service of the house. By solving the different equation of the model, we identify the equation that represents the premium, the price of having a better performance house one, that depends on the difference of prices and on this term on the right that corresponds to the share of houses with a lower level of quality than the house N. So the premium of class N is a decreasing function on the share of housing with lower class. In other words, the capitalization is driven by the scarcity of energy performance in the housing market. So we are trying to introduce this notion in which we compare not only the energy performance level, but the energy performance level in a context. So it's a dynamic perspective of this problem. So after this first model, we developed on a second step an econometric work. It's a spatiotemporal econometric approach. And we focus only on the market of apartments at a metropolis in France, Lyon. And we use as proxy of the energy performance the rating between A to G of the French energy performance certificate, that is a certificate usually in Europe. And we focus on the categorical information because in a previous work, we showed that the most of individuals read this information and not the numerical information. So the first class A is the most efficient one, and G the least efficient one. For this econometric work, we use 4 different sources of data: the notarial database that include transactions between January 2013 and December 2018. We have information as prices, latitude, longitude, the day of transaction, and other intrinsic information. We built a geographic information system in which we measure the distance between each apartment of our database to different kinds of amenities sources, like parks, banks, schools, hospitals, police stations, etc. And we complete that with a socio-demographic information on the neighborhood of each apartment. We have information about the rate of social diversity, the age of population, the rate of vacancy, etc. So quickly, I will say the metropolis of Lyon is a growing market. It's an important city in France. And we observe different price for urban and rural location. And we see, like in another European cities, that the central location present a higher level of prices. On this graphic, we see the distribution of prices for the different classes, and we can see that that seems to present different distributions. However, on the econometric work, we control for all the other characteristics of the housing. So as we see on the theoretical work, and by the fact that in the rental market and the real estate market, the spatial and temporal dimensions are really important, we use an econometric approach that takes into account of these dimensions. So we built a spatio-temporal neighborhood matrix in which we defined the weight between each apartment and all the other apartments on the database. And with this information, we test for the presence of a spatio-temporal autocorrelation. We show that effectively there exists this spatio-temporal autocorrelation in our database. And with this matrix, we measure also a neighborhood for each apartment. And in function of this neighborhood, we measure the level of scarcity for each one of our apartments that constitute our main variable. So here in the equation 6 and 7, I think, we have the specification used for our econometric spatio-temporal model, in which W is corresponds to this matrix of weights. Lambda is a parameter associated to the autocorrelation, and eta is a distributed error term. In X, we use a different set of variables, giving us information about the intrinsic information of the apartments. And we introduce the distance variable, and this variable associated to the energy performance of the apartments. So the EPC scarcity variable is defined as the rate of apartment with a lower level of performance in the neighborhood of each apartment. So it's a proxy of the scarcity of the performance, a relative measure of performance. So here we have the results for two models by using one of the different matrices. So on the left, we have a classic model used in the literature, but corrected for the spatio-temporal relation. And here, as you can see, the valorization for higher levels, A, B, C, is positive for this classic model, the classic STEM, in which we compare each class to a reference class D. So our results are consistent with the results of the literature. And on the right, we have our model that measures the relationship between the level of scarcity and the prices of apartments. So here we see different significant and positive coefficient for the highest classes A, B, C, and D. So with these results of the second regression, we build this graphic, and here we compare the premium for scarcity with the scarcity rates. We see on the right the highest classes, C, B, A, and here we have D and E. So as you can see, the most scarcest classes are on the right and are on the right, and we see that the relationship between this scarcity level and the prices of apartments is positive. So you can see the trend, and this is also consistent with the classic results on the literature. But this time we introduce this dynamic approach in the sense of this rating of scarcity could change, for example, with a renovation of a part of apartments of a type. So if we modify, for example, the rate of apartments of type D, level of scarcity that will change for the rating C, and the premium for the class C will be reduced. So if on conclusion, we have this positive effect of scarcity for these classes that we name scarcity patrimonial effect or Rargem effect. And it takes into account of a relative measure of the neighborhood. So it could be related to a case study, to different conditions of market. We can imagine that the increase in the number of energy efficiency renovation causes the potential financial gains in patrimonial value to decrease, therefore making such renovation potentially less attractive. So we consider that a dynamic approach of the green value is in this sense necessary to the public policies to anticipate the potential changing on this valorization premium that could be an effect of the market adjustment mechanism. And directly this work could help to explain in part the slowness process of renovation for different kinds of case studies. So thank you very much for your attention.
Thank you, Natalie, for this so very interesting work and very clear presentation, perfectly on time in the 15 minutes that the conference assigns to us. And it is very interesting. I have a lot of questions, but as I said, yes, the question and answer time will be in the end of this session. So thank you once again. And now, according to the program, our second speaker is Dr. Giuseppe Dell'Olio.
Good morning.
Good morning, Giuseppe. Giuseppe works for a very important Italian state-owned company, the one who is responsible to promote renewables and energy efficiency in Italy. And so it is very interesting for us to listen the presentation of his work about the assessment of domestic hot water demand. So thank you very much, Giuseppe, please.
Thank you for having me. Please confirm that you can see my screen. I tried to share it. I'm not sure it was also. Can you see my screen?
Not exactly. Now, yes, I see myself.
Okay. So, assuming that everybody is seeing it now. Good morning. My name is Giuseppe Dell'Olio. I work with GSC, which is a state authority for incentivizing renewables and energy efficiency. And today I would like to talk to you about the domestic hot water, or DHW, for flats and apartments.
But
you don't
Giuseppe,
see the
we cannot see
presentation.
the screen. No, we cannot see the shared screen.
Sorry. What is wrong with it? I'll try it all over again.
Yeah.
I get the message you are sharing the screen. So
yes, but it disappeared.
There is a black screen.
It disappeared.
Yeah, again.
I'll do it, or maybe.
Now we see.
Maybe now it's better.
It's better, but still it is black.
If you don't have the webcam on, it might not share.
Okay, but I turned it on. Ah, okay.
You have
maybe
to have
now.
it on.
Yes, it is on.
It is on, but we see a black screen. The message is that you activated the screen sharing, but the screen is black.
I'm sorry. What can I do? There's a button, stop share. I'll try to interrupt the share and start all over.
Yeah. Yes. Maybe.
How is it now?
Still the same. It's the same.
I'm not. I'm sorry. That was my best. I'll try to tell you the results just by voice.
Or maybe, if you want, we can.
Sorry, you have a problem with your webcam because we don't see you either. I mean, we don't see you. We don't see what you share.
Sorry, I'm seeing myself on our program. So,
no.
My webcam is working. I just don't know. Anything changed now? No.
No. We don't see you. And we see a black screen.
I don't know.
But also we don't see yourself. So yes, probably it's the webcam. Maybe we can change the order of the presentations if you think that
yes,
taking some time.
I try to change my device. Yes, if you don't mind, please change your presentations, and I'll be available.
Okay.
Soon, I hope.
Okay. If you,
I'm leaving, completely leaving now because I'm getting in with another.
yeah.
Okay. See you soon. See you soon. I'm sorry for this.
Okay. Thank you, Joseph.
Thank you.
And okay, so I will leave the floor to Dr. Salim Turdaliev from the Institute of Economic Studies, Faculty of Social Sciences, Charles University, Czech Republic, which will talk to us about price responsiveness and carbon emission reduction in the residential sector, evidence from natural experiments in Russia.
Exactly. Thank you very much. I just wanted to make a little point. I'm not a doctor yet. I'm a PhD student at the Institute of Economic Studies. So I'm going to present you the first chapter of my PhD dissertation, actually.
Thank you. We are honored of that. Thank you.
So let me share the screen. I hope it will work for me. Can you see it now?
Yes, perfectly.
Okay. So thank you very much once again to having me on this conference. Today I'm going to present you our joint work with Anna Alberini and Milan Shasny. And I would like to acknowledge the financial support from the grant agency of Charles University and the European Union's Jim Climb project for funding this research. So in this study, we have estimated the price elasticity of electricity demand in the context of a natural experiment. So our main contribution is that we estimate the price elasticity using the arguably exogenous variation in price, which results from the introduction of increasing block rate tariff in the 7 regions of Russia in 2013. And for this purpose, we use micro-level household data on Russia RLMS, which is Russian Longitudinal Monitoring Survey. So unfortunately, in the RLMS, we don't have information on all 7 experimental regions. What we have is information on 3 of them. So out of 7 regions which you see on your screens, we have data on Krasnoyarsky Krai, Nizhny Novgorod Oblast, and Rostov Oblast. So this constitutes about 10% of our whole sample. And here are presented the control regions. So overall, we have about 30,000 observations, and this constitutes 90% of these observations. Let me give a little information about the natural experiment itself. In 2013, Russia introduced so-called social norms for electricity consumption. So based on the type of the household income characteristics, number of people living in the households, each household is prescribed a so-called social norm according to which it is priced electricity. So if the household consumes below the prescribed social norm, it pays at the lower subsidized price. However, if the household consumes more than prescribed social norms, then it basically pays at the higher market price for the electricity. So this is some map for you to see how exactly the social norms are prescribed in the three control, in the three treatment regions for which we observe the information in our data. So, for example, so you can see that the social norm is actually different for each of the treatment regions. So in the Rostov, if you live in the urban area, for example, and there is only 2 people in the household, then your prescribed social norm will be 156 kilowatts a month. So if you consume below this norm, you pay at the lower price. If you consume above, you pay at the higher price. And then, depending on the type of the household, your social norm varies. So, and now let's talk about the micro data that we're using. We use panel data, Russian longitudinal monitoring survey, which is conducted by the Higher School of Economics and the Carolina Population Center in the USA. So each year, about 7,000 households with approximately 18,000 individuals are surveyed. So our study period covers years from 2010 till 2016. So actually, RLMS is conducted since 1994. Excuse me? I guess it was some random noise, right? Like it wasn't a question. Okay. Actually, RLMS is conducted since 1994, but we choose to study the post-crisis period of time because obviously the financial crisis could affect our results somehow. So we choose to study period from 2010 till 2016. And we also use regional weather data obtained from meteorblue.com. So this are the sample statistics, characteristics of the dwellings under the study. So here you can see the characteristics in control regions. Here you can see characteristics in treatment regions. So we see that the sizes of the dwellings are approximately identical. However, the treatment regions are more urbanized. So 93% as compared to 73% approximately. And we also have information on whether the household is connected to the central delivery of gas, heating, hot water, and etc. I also presenting you the respondents characteristics. So respondents characteristics are more identical than characteristics of the household. So the average incomes are almost exactly identical. So those are the monthly incomes corrected to the 2016 rubles. So ruble is the national currency of Russia. We see that the levels of education are also almost identical in our sample. And the average number of people in the household are less than 3. So we also have a very rich data on home appliances. So we see that actually there are some discrepancies between control and treatment regions here. So we see that a freezer is owned by more people in treatment regions than in the control region, for example. the same holds for electric stove, and basically discrepancies and on these like large discrepancies and on these other home appliances are basically identical. In this study, we actually use a two-stage least squares in order to estimate both price and. So why we use a two-stage least squares? Because in the case of increasing block rate tariff, the price is actually endogenous because it is a function of your consumption, actually. So therefore, here we use the instrumental variable and we instrument the price with a full tariff schedule. So we actually run two-stage least squares. So ln E stands for the logarithm of electricity consumption. ln P is a log of full tariff schedule, and in this case, as you will see in my results, we have about 35 cutoffs because we have different types of households, and therefore the cutoff is different for each and every of these households, and in total we have 35 instruments here. So we also have data on benefits, weather variables, and some extra time varying controls, because here we are actually estimating it using a fixed effect because we have a panel data. So here we run two types of two-stage least squares. So first, we run just two-stage least squares based on clustered standard errors, and standard errors are clustered on the household level. Here we see that we have almost 30,000 observations. We have 32 instruments, and Hansen-J statistics of exogeneity of our price variable is actually insignificant, which clearly states that we should have used instrument in this case. So we see that the log of price is the coefficient of log of price is almost minus 0.10, which is in accord with other estimates from the transition economies like Russia. And we also see that the 0.38, which is approximately 4%. So it's also in accord with other studies. We see that besides those two main variables, family size is highly significant, some weather variables are significant, and benefits and discounts received for the utilities are actually insignificant determinants of household consumption. So here we were forced to not to include the household appliances data because it turns out to be correlated with the income variable. So we don't include these variables here. So next, we also run two-stage least squares after applying coordinate exact matching procedure on our data. So in this case, we first match the identical household in the treatment and control regions, and only after this, on this data, we actually run two-stage least squares. So after applying this procedure, we see that most of the observations were actually matched to each other. Only 3 observations were not matched from the treatment region. And we see that the results are almost identical, except that our coefficient on price is slightly lower and less statistically significant. So in case of just two-stage risk curve without any matching procedure, it was statistically significant at 95% and close to minus 0.10, while here it's statistically significant only at 90%, and it is minus 0.071. So next, we also ran some policy simulation using this estimated coefficient. So what we did is as follows. What would be the reduction in electricity consumption and thus reduction in CO2 emissions if identical IBR policy were to be implemented across whole Russian Federation? So for this purpose, we use elasticity estimate of approximately minus 0.10, and according to our calculation, the average electricity reduction in these states, in this treatment states, was 10%. So if we want to calculate the CO2 emission changes, we also need the composition of the carbon intensity of electricity generation across whole Russia. So we obtained some data from McKinsey for this purpose, and the generation in Russia is actually divided for 7 main regions, and the carbon intensity of each as follows. So 2 main sources of electricity in Russia are, not surprisingly, gas and coal. So using all this information, we estimate that the average electricity reduction in a typical Russian household will be equal to approximately 25 kilowatt hours a year. So it's a very small reduction, unfortunately, which will account if we multiply it by the total number of households in Russian Federation, which is 55 million approximately, is equal to about only 1% of the total consumption of electricity in Russia. We also estimate the CO2 reduction, which is 17.76 kilogram of CO2 in a year again. And if we again multiply it by 55 million households in Russia, it is only equal to 0.06% of the total CO2 emissions. However, if we compute the change in the revenue from the introduction of this policy, we will see that the state of Russia will receive approximately $700 million additionally each year if the same policy, if the same IBR policy will be implemented across whole Russia. So this is all. Thank you for your attention.
Thank you very much, Salim. Very interesting. very interesting. And you underlined again the importance of the dynamic of the time dimension in the human life and in energy modeling in a complex world. Yes,
Thank you very much.
Yeah, thank you. And I will leave the floor to okay, I see Giuseppe again.
Yes, if you want, I can try now or later as you think is better.
Yeah, since we can see you properly, I think you can try.
I'm now trying to share my screen. I should be here. Oh, I'm sorry. Maybe you can go on with another presentation. I'll choose my files. The first time I use it this way. Sorry for this.
Okay. No problem. So I leave the floor to Francesco.
Good morning again. Okay, now I try to share my screen. You should my screen and you should hear me. Okay?
Okay.
Good morning, everyone. Again, I'm an engineer of Studio Santi, that is an energy management and consulting engineering firm in Rome, owned by Professor Santi. And I will present you a case study, a special case study, because it is about a 100-year-old building in Rome. The title of the presentation is Energy Efficiency in Public Historical Buildings, an Integrated Approach, the case of the National Gallery of Modern and Contemporary Art in Rome. This work was made by me with Federico Santi and Romano Alberto Acri. We start from the beginning. We know that the minimum target for humanity is to keep below 2 degrees Celsius the global warming. It means to halve carbon emissions by 2050 and to zero them by 2100. If we don't succeed in this, we will experience serious problems such as sea level rising, famine, and malnutrition. Efficiency is the most important driver towards the below 2 Celsius degrees scenario. The 44% of the global carbon emission reduction in the sustainable scenario is delegated to efficiency. So efficiency is more important than renewables. The buildings and construction sector is a key actor in the fight against climate change because it accounts for 36% of final energy use and 39% of energy and process-related emissions. Buildings' final energy demand is rising, but carbon emissions are lowering. From 2010 to 2017, floor area increased plus 17%, and population increased plus 8%, but carbon emission increased only 4% and energy consumption only 5%, thanks to power sector decarbonization and enhanced energy efficiency in buildings. But global energy efficiency investments on buildings are still too low, and we can do better. In 2017, only 400 of $5,000 billion, that is the total spending on buildings, has been spent on energy efficiency. Half for improvement of building envelopes and 25% for intervention on the HVAC. So the renovation spending is 0.1 times compared to the new construction spending. But is it true for every part of the world? And what happens in Europe and in Italy? In terms of buildings, Europe is very different from the rest of the world. For example, in Europe, the density of cultural UNESCO sites is much higher than any other part of the world. Each dot in the map represents a UNESCO sites that are mostly historical buildings. And this data can help us to understand how different is Europe from the rest of the world. Higher number of old buildings means stronger need to renovate them. Italy is slightly different from the rest of Europe because it has the highest number of UNESCO sites of the world, the same number of China. But China is 23 times in population and 32 times in extension compared to Italy. but that's the same number of UNESCO sites. Other European countries follow Italy, like Spain, Germany, France. So in terms of buildings age and characteristic, Europe is very different from the rest of the world, and Italy is the most significant case of this difference. In Italy, buildings renovation are much more than new construction. Since the 2008 crisis, the yearly investments in renovation of buildings are higher than the new construction because the government incentives also help to keep alive the building sector during this crisis. So in 2017, in Italy, the renovation investments were 3.5 compared to the new construction investments. This ratio is very different from the 0.1 global ratio seen before. Why? Because Italian building stock is one of the oldest in the world. 6 out of 10 houses are older than 50 years, and 2 out of 10 schools are older than 100 years. So Italy needs to deeply renovate its building stock, both private and public, and it is slowly happening. Italian professionals know how to deal with historical buildings, therefore they should pave the way in this specific sector. And now the case study, an integrated approach for the National Gallery of Modern and Contemporary Art in Rome. It is a 100-year-old Italian museum that is going to become a case study of energy efficiency in public historical building. This is the largest Italian modern and contemporary art collection and one of the most important museums in Rome. It is made by 2 buildings. The building that is today a museum is the Bazzani building, the big one. It is a 100-year-old building designed by Cesare Bazzani for 120,000 cubic meter, 55 exposition rooms, and 1,100 artworks, and more than 200,000 visitors per year. This museum has almost €1 million of energy costs, and to balance the greenhouse gases emissions of the museum, it needs a forest as large as 3 times Villa Borghese Park in Rome, that is the largest park in the city of Rome. The energy consumption of the museum are mostly electricity for 2,400,000 kilowatt hour per year for lighting, pumps, air handling, fans, and devices. Natural gas, 850,000 cubic meter per year for building heating and cooling, for a total primary energy consumption of 1,175 TOE per year. The energy use index of the building, the EUE, is 116 kilowatt per year per cubic meter, and the annual energy cost of the building is 980,000 euro per year, and the annual equivalent carbon emissions are 2,600 tons per year. From the UNWTO to the energy efficiency integrated approach. Everything started in 2017 when the National Gallery, thanks to its director, Cristiana Collu, joined the International Year of Sustainable Tourism for Development, promoted by the UN World Tourism Organization. With this project started the energy efficiency rules of the museum, conceived as an integrated approach made by different parts related to many aspects. This integrated approach that was conceived and curated by Studio Santi is composed by the energy diagnosis of the museum, the design of energy efficiency works, such as new central heating and cooling system, new air handling system and high reflectance roof, new photovoltaic skylights, and also obtaining government incentives like Conto Termico, the energy management of the museum, the implementation of an ISO 50001 certified energy management system, and the near zero energy building renovation of the Cosenza building. All these things respecting the historical architectural constraint of the 100-year-old building, and this is the toughest challenge. We start with the first intervention, that is a new central heating and cooling system from fossil fuel with 3 natural gas boilers for heating and 3 water lithium bromide vapor absorption refrigerators for cooling, to mostly renewable energy with 4 air water heat pumps and inverter controlled electric motors. The second intervention was the new air handling system and high reflectance roof from old and wrong installed AHU and air ducts and traditional tiles roof to a new efficient and well installed AHU and air ducts and air reflectance roof with a solar reflection index more than 100. And then the new photovoltaic skylights from old fragile and often broken traditional glass layer to a new and stronger glass layer with integrated photovoltaic plant with a 20% light transparency. This is a sample of the building integrated photovoltaic, the BIPV. The expected results of the three interventions will be a minus 61% in energy consumption, a minus 48% in energy cost, and minus 68% in greenhouse gases emissions. It means 2 times the Villa Borghese Park in Rome. And also the new heating and cooling system has a payback time less than 3 years, and we won't have natural gas in the museum, that it can be a problem for firefighting. So the integrated approach doesn't stop here, but it is completed by other energy efficiency actions, such as obtaining government incentives like Conto Termico that is managed by the GSE and encourages with 900 million euro per year interventions to increase energy efficiency and production of thermal energy from renewable sources for small plants. The beneficiaries are public administration with 200 million euro per year reserved for public buildings, but also companies and individuals. The new heating and cooling system with 4 air water heat pump of the National Gallery of Modern and Contemporary Art is partially financed for the 40%. It means 475,000 euro by the Conto Termico government incentives. And then the energy management of the museum. This process helps to monitor energy system performance and energy cost, taking action when necessary. The monitoring of cooling system efficiency index showed a severe increasing of the normalized summer consumption in 2018. So with the cleaning of the vapor absorption refrigerator during the following winter in 2019, the performance improved again. The monitoring of the cost of natural gas showed a severe increasing of the unit price of energy component in 2018 due to a changing in the contract condition. The energy manager helped the procurement office of the museum to sign a new cheaper contract, and in 2019 the unit price decreased. The ISO 50001 certified energy management system. The National Gallery is the first Italian museum with an ISO 50001 certified energy management system. Here we can see the ISO 50001 in the 2011 version and in 2018 version. And this is the natural outcome of the integrated energy efficiency approach of the museum. And then last but not least, the NZEB renovation of the Cosenza building. That is a building currently not used, is in the back of the museum, and it is going to be renovated as an NZEB, so a near zero energy building. So this process aims to transform a 17 building in a nearly zero energy building. In conclusion, we can say that efficiency is more important than renewables to reach the below 2 Celsius degree sustainable scenario, and the buildings and construction sector accounts for 39% of the global carbon emission. Globally, the renovation spending is 0.1 compared to the total building and construction spending, but in Europe it is different, especially in Italy, where renovation spending is 3.5 times compared to new construction spendings. Why? Because we need to deeply renovate our building stock, both private and public. Italian professionals know how to deal with historical public buildings, therefore they should pave the way in this sector. And the case of the National Gallery of Modern and Contemporary Art in Rome showed that it is possible to make more efficient a 100-year-old historical public building, but only through an integrated approach. This approach starts from the energy diagnosis and the realization of action to decrease the impact of the building in terms of energy consumption with an expected minus 61%, greenhouse gases emissions with minus 68%, and energy costs with minus 48%, but it also includes many other actions like obtaining government incentives, energy management, ISO 50001 certified EMS, and etc. to make it possible. Thank you.
Okay, thank you, Francesco, for this very interesting presentation and practical case study. I am touched again by this fact that brilliant young researchers underline the importance of time, in this case years or centuries, in all this big issue of emission reduction. Yes, we have to think dynamically. You remind us that we have to think dynamically. Okay, thank you again. And the last presentation we will try with Giuseppe now.
I try once again. I don't know.
No, unfortunately, we cannot.
I'm sorry. This time, documents. I don't know why No, I'm really sorry. I have a problem.
I think that maybe if you cannot share your screen, by the way, you can talk to us a bit about the main issues.
But maybe, are you seeing anything right now?
Not now, but before we were seeing you. Maybe Natalie has a solution.
Maybe you can share with us your presentation if you need to present in graphics, image, or something like that.
Yeah, that's
no. It's only written stuff, so I can just tell this to you.
Okay.
I'll do my best in this way. Okay, I'm going to talk to you about the assessment of domestic hot water demand, and we checked a few criteria that are used nowadays, widely used, but are theoretical. We checked them against some real-life data which we had available. So, first of all, the theoretical approaches that we checked against real-life data were one based on standard UNI TS 11300-2, and the other was a European standard EN 15450, heating system in buildings. The first one, UNI TS 11300, assumes that the bigger the apartment, the more numerous are the occupants, and the more DHV, domestic hot water, is needed. So the first thing to do is to check whether this approach is correct. So domestic hot water is assumed by this TS 11300, is assumed to increase approximately linearly with the apartment area, except where very large or very small areas are involved. Very large meaning more than 200 square meters, or very small, less than 50 square meters. In these two cases, domestic hot water demand is assumed to be constant. In all other cases, it is assumed to vary linearly with the area, the useful area or the flat. So to check whether this criterion was reasonable, we evaluated 45 methane-fired central heating installations in apartment buildings in Italy. Each one of these boilers provides both heating and domestic hot water production. The total volume of the apartments considered was 438,000 and more cubic meters, so quite a large sample. And this amounts to something less than 2,000 average size dwellings. More precise is 1,900. The above central heating installations, have been monitored for several years, from 2011 to 2016, as a whole. Not all boilers have been working at the same time in this long period, but that's when monitoring started and finished, 2011 and 2016. Two quantities were considered, namely heat produced, kilowatt hours, and fuel consumed, and this for each boiler. From now on, I will refer to the data collected as actual operation data, or AOD. And first of all, we performed a very similitude analysis to check whether these data were accurate or reasonable. We defined a load factor both for each individual boiler and for all the boilers as a whole. For each boiler, the load factor is the ratio of heat that was in fact actually produced during the monitoring time, ratio to the maximum heat that could have been produced. And the maximum heat, in turn, is the product of boiler power, which is known, times monitoring time, hours. This for each individual boiler. The overall load factor, on the contrary, is a weight average of individual load factors, weight being the respective maximum heats that could have been produced. So hypothetically, if all boilers had been constantly operated at full power or at rated power, all individual load factors would be 1, and so would also the overall factor, of course. In real life, however, DHV load profiles are far from constant. We have very high peaks for short times, this is hot water, let's not forget, and zero load for long time. So as a result, average load is much lower than peak load, and the average to peak ratio is low. So we expect to have a low load factor. Well, in average, we found a load factor of 0.178, so very low. This confirms expectations. Operation data we collected are realistic, so we can go on with our analysis. We also calculated overall efficiencies, including both heating and domestic hot water reduction. And not surprisingly, a few efficiencies turned out to exceed 100%, which is consistent with the ever-increasing spread of condensation boilers. It's normal for at least a few efficiency to exceed 100%. The lowest was 0.92, and the highest was 1.116. Well, this latter was regarded as possibly inaccurate. It's much more than 100%. And therefore, in the following analysis, we also excluded this and a few other unrealistic figures. DHW consumption, domestic hot water consumption, all included, turned out to be 42.68 kilowatt hour thermal for square meter and for year. this with all boilers included. After excluding a few suspect ones, the DHW consumption became 41.79 kilowatt hours thermal for square meter and per year. So the difference is some 2%, which is comparable to typical measuring instrument errors. We conclude that the result is highly robust and reliable, because after excluding a suspect inaccurate case, nothing changed or very little changed. In the end, we checked for correlation between building useful area and yearly domestic hot water heat production. The correlation turned out to be very strong. Correlation coefficient was 0.92, so very close to 1, which would be perfect linear correlation. So we concluded that DHW consumption is in fact proportional to useful area. And now we had to choose a proportionality coefficient. Anyway, the first conclusion is that UNITS 11300 criterion is realistic. Anyway, when the most common areas are concerned, namely between 50 and 200 square meters. The above results, the results from actual operation data, were based on following conditions: climate zone E, which in Italy is the second coldest, draw-off temperature, so temperature at which domestic hot water is used, 53 degrees centigrade, and cold water temperature, the temperature at which water is provided to the apartment, 10 degrees centigrade. We got an average overall consumption of 138,000 kilowatt hour per year. So there's no surface here. This is not for square meters, but it's the overall data. The correlation coefficient, or I already mentioned, was 0.92. The coefficient was 41.68 kilowatt hour per square meter and per year. This is a regression analysis, you see, and there is also an intercept, which is not interesting. Probably what we called here beta 1, the coefficient, is the most interesting data, which is very close to what I already mentioned, 41 point something against 42 point something. So we conclude that UNI 11300 is realistic, but the coefficients are not and should be reviewed in the next edition of this, in the next release of this standard. Estimated consumption, estimated based on 11300, turned out to be 66% of operational data. So a strong underestimation. A more precise assessment is that based on a European standard, EN 15450, which does not refer to surface. So we had to introduce a surface somehow. We chose for this the average size of flats, the average useful area of flats in Italy, which is some 76 square meters. And with this estimated data, estimated meaning based on 15450, turned out to be some 11% more than actual operation data. So there is a slight overestimation, which is good when it comes to dimensioning installations and buildings. Just a few words about how 15450 is conceived. It assumes a number of consumptions of water for an average family, or for several families. We choose the average one. a family of 3 people with bath and shower use, well, for each hour of the day, consumption or more consumption of hot water are hypothesized. So, for example, in the morning, there is a bath. At lunchtime, there is a dishwashing. In the evening, another bath, showers in between, and hand washing somewhere. I will not get into details about this. But this allowed us to estimate the daily consumption, the daily hot water consumption for a family of 3. We then turn this into a yearly consumption just by multiplying by 365. So we were able to make a comparison with the operational data. We had, of course, to adjust for the temperature difference between hot water as used and cold water as provided. We chose the interval 60 to 10 degrees centigrade for all considerations. Well, in this case, as you see, we have a slight overestimation, which is good. We can do even better. We changed the EN 50450 daily pattern by replacing 1 bath with 1 shower, which is probably more realistic nowadays. It's quite not likely to have 2 baths in 1 day. Shower is more used. Well, with this modification, estimated data turned out to be 90% of operational data. So EN 15450 is a good approximation, is a good estimate in itself, and is probably an even better one with this slight modification I mentioned. So, conclusion, domestic hot water yearly demand of an apartment can actually be regarded as proportional to the apartment's useful area, in the most common cases anyway, and based on measured data, a sound assumption for the proportionality coefficient is 43, a bit more than the figure I mentioned, just to round up, 43 kilowatt hour thermal for square meter and for year. This is based on a 53 degrees centigrade draw-off temperature and a 10 degrees centigrade supply temperature from the public means. So UNI TS 11300 is based on a reasonable and realistic assumption, but the coefficient it uses are not realistic, and they underestimate the consumption. The closest prediction, on the contrary, that we have for the operational, the real life data is provided by EN 15450 in its table E.4. And this, the standard features good accuracy and is conservative. Besides, after a realistic modification, a bath replaced by a shower, this becomes a very close underestimate. I think this is enough. I hope you could get something of what I said. I'm sure this was not easy, because not having something written under the eye can be tricky, but I apologize for any inconvenience, and I'm available to any clarification now or in the future. Thank you very much.
Thank you very much, Giuseppe. It has been a very clear presentation despite all the difficulties, and I took notes. I took notes of what you said, which is very, very important, I think. And if we think that the DHW, maybe it is nowadays the only energy storage system already in place, yes, in the houses. So right. I think
we all talk about storage, but the actual storage only happens in hot water nowadays.
Yeah,
so.
Exactly. Nowadays, that's the only device we have in this sense. But it is very interesting, very, very, very interesting. Thank you very much.
Thank you much. I hope so.
Thank you.
Thank you all for your attention.
Yeah. So now we have about 15 minutes for question and answer time. Not much, but at least some questions we can share. And I would prefer to leave the floor to you, dear speakers, if you have cross questions for the presentations. I leave you to break the ice.
So maybe I will start with a question to Francesco.
Perfect.
I wanted to know if which kind of firms develop that kind of renovation on public patrimonial buildings, and if it's possible that the firms work, for example, on the other kind of buildings by energy performance contracts. Yes, I don't know if it's the same kind of firms or it's different.
Thank you. Yes, the EPC is a solution to develop this kind of intervention. It was not the case of our intervention in the national galleries, because they wanted to manage these works without a contractor with an EPC contract. But sure, it is a way to develop these interventions, to raise funds to make this intervention. And we know in the next years, even after this COVID emergency, we will ask to public administration to spend, to make investments. And one way to make these investments, I think it could be the renovation of the public building stock. In Europe, especially in Italy, public building stock is very, very old. So they should find a solution, and they should use, I think, the integrated approach that we propose in the museum, because in this way you can obtain -60%, -4%, so very large results, also in 100 years old building. So yes, I think EPC can be a solution for sure.
Yes, I think this really interesting, because the renovation of the public buildings can allow us to develop an offer that could be generate transfer of mechanisms of renovation for houses, apartments, and other kind of buildings with a global vision of the renovation. So thank you very much for your presentation. It was really interesting.
Thank you. Thank you.
Yes, it's a very good question to have this sector of public building as a driver for energy efficiency. Yes. Supporting the energy service company to have a portfolio of projects, diverse projects, I mean, in the public sector, but also in the private sector and the apartment. Yes. It's also a way probably to reduce the risk, to have a portfolio projects of energy efficiency intervention. Yeah, any other questions?
Maybe a question for Giuseppe Dall'Olio. The
Please.
TS in the UNI means experimental time. So will we have a new release of the UNI 11300 in the future or no? Thank you. I don't know if you know.
Well, I'm not directly involved in updating this TS, but to my knowledge, TSs by the nature are due to be reviewed every 3 years. So the last edition should be, there was one in 2014, one in 2017. So probably one is being released right now. So at the latest, in 3 years, there should be a new edition. So there is allowance to review these coefficients, if of course this is deemed appropriate.
Thank you.
Thank you. More questions? For me, I have one question for Natalie, as promised. I wish to ask if it has been measured an impact of the price of energy commodities in your model, also in terms in dynamic terms. I mean, if changing the price of the energy commodities in time, it affects somehow the behavior of the model, or maybe it's just one of the variables.
Yes, we take that as a parameter, and we focus only on this on the premium for a different level of performance. So, but I think it's really a really interesting question, because it's linked, so that could yes, it is possible to test it in the future works. Thank you. Thank you very much. Yeah. For the moment, we didn't test it.
Okay.
On the economic work, we control for other kind of things that could be assimilate to that kind of information. Maybe, yes, we have to work more on the link between these two kinds of models that allow us to talk about this scarcity effect, but differently. So yes, we are working on it.
Yeah, great. Very interesting. Yes, I think that for maybe for households, the change of energy price is not very significant, because the structure of the price is mainly covered by taxes or other fixed elements. Yes, but when you switch from a commodity to another one,
yes.
For example, if you pass to electricity from natural gas or something like that, maybe it can have an effect maybe on the behavior of the model. Yeah.
Yes, maybe. Yes. That could be interesting to test it on the model. Yes. Thank you.
Yeah. Thank you, Natalie.
And maybe I will make a question for Salim. So I don't know if you're there.
Sure, yeah, of course I'm here.
Thank you very much. I don't know your case study perfectly and the conditions on this market, but it was more, I wanted to know how did you build the different treatments? How did you choose the treatment? You have only one, or it was composed by cities who...
Yes. Actually, it was the initiative of the government to start this IBR policy in 7 regions of Russia, starting from September of 2013. Right. So out of total 37 main regions in Russia, they implemented this policy in 7 of them. And but we don't observe a data for all 7 of these regions, only for 3 of them. Okay. Yeah, so this is experiment implemented actually on the regional levels. Okay. To answer your question.
Okay.
So if I understand, the dynamic tariff has a little effect on emission reduction in buildings in those regions, according to your calculations.
Yes, the thing is the electricity is still highly subsidized in Russia, and therefore it is relatively cheap. And that's why we don't have such an effect of the increase in price, because still it's relatively cheap. And one more thing is that households in Russia, they basically don't have too much appliances at home, like in some Western countries. Therefore, they cannot adjust their consumption much as well. Yeah.
I understand. So, do you have an idea of the policy consequence of this observation? I mean, is there any other solution to address the emission reduction in those regions in the household sector?
As you saw, like we ran a little simulation to see how much CO2 emissions would be if this kind of policy would be implemented in all 37 regions of Russia. Unfortunately, this reduction was about less than 0.5%. Yes, so therefore, I think this increase in price is still not enough to somehow adjust people's behavior. On the other hand, we cannot recommend to increase price too much because,
no, of course,
yes, the people in Russia cannot afford to pay the market price for the electricity, and therefore it is actually highly subsidized by the government.
Yeah, so probably the only solution is to change the carbon intensity of the energy commodities.
Probably, yes, because as you saw in my presentation, like majority of the electricity production comes from gas and coal, right? And probably they could change the intensity as you recommend.
Yeah. Thank you very much for your interesting perspective. Very interesting. Yeah. Other questions? We have not more than 5 minutes before the coffee break. At a distance, you know, that's a pity. Yeah. No, I don't know. I have a general question, but mainly for Giuseppe. When I was joking about the energy storage made by DHW, do you think is it possible in the future to control the DHV devices somehow, to give flexibility to the grid, to the power grid, to the power distribution grid? Yeah.
Yes, I see what you mean. Yes, it's possible, but it's a long way to go, in my view, because domestic hot water is very much connected to the habits of the inhabitants of a building. So I can imagine a centralized DHW storage system, one for a building or one for a block, for example. So in that case, statistically, the behaviors of different people would trade off each other, and that would provide a more constant availability of energy to the grid or for the grid. So yes, I confirm it's probably possible, but not now.
Yeah, academic for now. Yeah,
for now, academic. But why not? Let's think about it. Thank you. It's a good idea.
Yeah. Okay. So thank you very much. I think that we can close our session perfectly on time. It's really a great pleasure to have you here for us at AIEE in this symposium, and this session is session number 1. So you know, we have been the number 1. We made the experiment also. Yes, and yeah, I think that Natalie has been the first speaker in the whole event. Yeah. And yes, I see. You see how many perspectives on this issue of emission reductions from buildings. It is really complex. It is really complex and multidisciplinary approach that we need. But yes, it's the same that we are seeing in the pandemic world. That the only way to manage the complexity is to study. Yes, education is the key. So Yes, yes. So I'm very happy to see so young, brilliant researchers with us addressing the future of our energy system. Thank you very much for being here with us. Enjoy your conference.
Thank you very much. Thank you for having us.